All right, so this is for that mixed stoichiometry work that you have to do on page 79 and page 80. I'm going to go over this with you here so you can kind of get some extra help on this while I'm gone for the day. I am not going to go over and do the work for you. I'm not going to give you the answers. Now, if you want to know if your work is done correctly, you can check the answer key. Remember that was sent to you over an email several weeks ago, so you can go into there. If you don't have it, have somebody else forward it to you because there are plenty out there circulating around. So you have that, so you can check your answers using that answer key. What I want to do here is help you set up the process to be able to get the answer, help you read through a problem and understand what it's asking you to do. First, let's go through the 3 different questions that we always ask ourselves when we're doing a stoichiometry problem. The first one, and we have used a little bit different language this year than what's on this guide. The first one we said convert to moles. And that's the same question. You ask yourself how to get to moles, and you have these different things that you could possibly use. You could convert it to moles by having a mass. You can use Pivnert. You can use the molarity equation to calculate moles, or it could already be in moles. The next question is the mole ratio. This is the stoichiometry step. This is how we get from one thing to another in a chemical reaction. And then what does your answer need to be in? This is what we have said, convert out of moles. So those are the 3 questions we're going to be asking ourselves every single time we do a problem. I'm going to put them over here on the right-hand side so that we can refer to them as we go through each of these. And then hopefully this will be enough to get you going. All right. So here's the first one. We have nitrogen gas react with hydrogen gas to produce ammonia. That's what this thing here is ammonia. And it gives us some information. Ammonia is a very important agricultural compound. Without it, farmers would not be able to grow the crops to nearly the yield that they do. So this is very useful in agriculture. It's commercially produced through this synthesis reaction at very high temperature and pressure. So all of this so far is background information. This gives it a real-world scenario. It provides us with a reason why the ammonia is important, but for our calculations, it's extra information, so we don't need any of that. What we can do, though, is look at the rest of it and see what we need there. We have 400 liters of hydrogen gas with excess nitrogen. Remember, if it says excess nitrogen, it just means there's enough nitrogen to be able to react. We don't need to worry about it. What mass of ammonia would be produced if the conditions are 200 atmospheres and 900 degrees Celsius? First, the questions or the steps, convert to moles. And we have the mole ratio. Then we convert out of moles. So if we look at this problem, I'm given a volume. That is my key to use this. Because Pivnert has the volume in it, and it can calculate moles. We want to make sure that we don't use molarity, which also has a volume in it, because we're dealing with gases. Oops, that's what we're looking for there at the end. We're dealing with gases. We have 400 liters of hydrogen gas. So we're going to use Pivnert because that's our gas equation, not molarity. The second step then is our mole ratio. We're going to go from hydrogen gas, which is 3 moles, to ammonia, which is 2 moles. So I'll set up our mole ratio like this. We start with hydrogen gas, so that 3 moles of hydrogen gas is going to go on the bottom. We're looking for the moles of ammonia. So that goes on top. Then step 3, convert out of moles. We're looking for a mass. So we simply take the moles of the ammonia and convert it into mass of ammonia. We use the periodic table to get this. I might be going through these a little bit more quickly so that this video isn't 3 hours long, but I do want to make sure that you get enough to be able to work on these. Again, step 1, convert to moles. 2, mole ratio. 3, convert out of moles. We have solid carbon tetrabromide and fluorine gas. So if we look up here at the reactants, we have carbon tetrabromide and we have fluorine gas. It's a violent reaction that can produce carbon tetrafluoride and bromine liquid. So here's a tetrabromide, bromine, and tetrafluoride, fluorine. And then we have bromine liquid. What mass of carbon tetrafluoride would be produced given 5 grams of carbon tetrabromide and excess fluorine? Remember that we don't have to do anything with that. So this one is just a mass to mass equation. Since we have a mass of carbon tetrabromide, we're going to take that mass of carbon tetrabromide and convert it into moles of carbon tetrabromide. In the second step, so that's our question, how do we get to moles? We just convert it using the periodic table. Then we can do the mole ratio between carbon tetrabromide and carbon tetrafluoride. So we're going from here to there. And then we have step 3, where we can then take the moles of that carbon tetrafluoride and convert it into mass using the periodic table. So those are our 3 steps there. All right. Number 3. Let's get these over here again. Oops. Wasn't thinking. So those are 3 steps. Nitrogen triiodide is kind of a fun compound. It's very unstable. If it's dried and just touched with a little feather or just a large clap, it will explode into nitrogen gas and iodine gas. So if we have 10 grams of this stuff, what volume of nitrogen and iodine gas would be produced? So we have 2 different problems here. We're looking for the volume of nitrogen and volume of iodine, but both of those are volumes. Given 10 grams though, so our first step is to convert that to moles. So we're just going to use our grams of our nitrogen triiodide and convert it into moles using the periodic table. Second step is the mole ratio. We go from then moles of nitrogen iodide to moles of nitrogen. And then we also have to do another problem, moles of nitrogen triiodide to moles of hydrogen. So we have 2 separate problems we have to do here. In step 3 though, we're just using pivnert. Once we have moles of nitrogen, we can plug it in. Once we have moles of hydrogen, we can plug that in as well. So those are the 2 things we can do there. All right. Next page, this is going to be page 80. Let's get these up here again real quick. And I'm actually going to see if I can do both of these together so I don't have to erase this again. So when I erase the whole screen, this goes away, which is kind of unfortunate. All right, we have aqueous lithium fluoride and lithium carbonate. So both of these are aqueous. So look here, we have these two things here. There's the aluminum trifluoride or aluminum fluoride. Here's a lithium carbonate. Those are two reactants to form the solid precipitate magnesium carbonate. Ooh, that is a typo. That is aluminum. Is that one fixed on your page? It is. This is an old version. You have the new version. And we double check to make sure everything else is correct here when we go through this. So we're producing that solid aluminum carbonate and aqueous lithium fluoride. So if we have 50 milliliters and 0.5 molar solution of this stuff, that's our aluminum fluoride, and we add that to this, concentrated means that it's going to be the excess reactant, so we can get rid of that information. What mass of the, and I'm going to guess this has changed as well, yep, it is, aluminum carbonate will be produced. So we can go through our steps here. First step is convert to moles. To do that, we're going to use the molarity equation. Moles over liters. We can put our 0.5 molar in for the molarity. We can plug in the volume for the liters and solve for moles. Then we can go through the mole ratio, which is going to be our moles of aluminum fluoride to the moles of aluminum carbonate. And then we have the last step, which is to convert to a mass of that. So we simply take our moles of it and convert it into mass. And we're good. Number 5, given that same 50 milliliters of 0.5 molar solution of aluminum fluoride, what volume of the 0.35 molar lithium carbonate would be required to completely react? So now we're going to stay on this side of the equation. From there to there. And we're looking for a volume in the end. So this is going to be a little bit different. We still use molarity. It's going to be the same start. Like you've already done this step, it's still the same step. Then we go on to the second step, which is our moles of aluminum fluoride to moles of lithium carbonate. Once we have that, we can do another problem for molarity. Molarity is moles over volume. So we have our moles. These moles can get plugged in here. And we have molarity, which can get plugged in there. So then we can solve for volume. Remember, we practiced solving for volume earlier on in the week. All right. We're still dealing with the same reaction. In this case, we have 100 milliliters of the lithium fluoride and 100 milliliters of the lithium carbonate. If we have 2.1 grams of the aluminum carbonate is produced, what is the concentration of the lithium fluoride? And assume that both of the reactants react completely. This one is a challenge problem. This one is quite difficult for us. We haven't worked with ones like this before. So I am not even going to do any work here for you. If you want to work on this one and see if you can get the answer is in the answer key. Otherwise, I can work with you individually if you want to do this one. This one is not going to be one that I expect you to be able to do. All right. We have the last two problems that we're going to look at. Hopefully you can still see my convert to mole here, mole ratio and convert out of moles. We have this problem here. All alkali metals react violently with halogens to produce a salt. So here is our salt of potassium chloride. It's a solid. Given the reaction above of the potassium metal and the chlorine gas, what mass of the potassium chloride would be produced if we have 17 grams of the potassium and excess chlorine? So first thing I'm going to do is cross out this excess chlorine. We don't do anything with it. We have a mass of potassium, so we take that mass of potassium and convert it into moles of potassium. We take the moles of potassium and convert it into moles of potassium chloride. So that's what we're looking for here, what mass of potassium chloride. Number 3, we take the moles of the potassium chloride and convert it into mass of potassium chloride. So those are our 3 steps there. Finally, the last question, how much potassium would be reacted if 6 liters of chlorine gas was used at 2.5 atmospheres and 30 degrees Celsius? So again, I have this is from the first problem. I have 6 liters of a gas. That tells me I have to use Pivnert to get moles. There's my moles. The second step is to take the moles of that chlorine gas and convert it into moles of the potassium. Finally, I take the moles of the potassium and convert it into mass of the potassium. And then we have our final answer. All right, ladies and gentlemen, hopefully this helped you. If you got stuck on any of these, remember that question number 6 up there is a challenge problem. Feel free to work on that and get some challenge for that kind of a problem, but I do not expect you to be able to do that one.